Welcome to a rundown on the molecular modeling experiment that deals with working with Spartan molecular modeling software. This will give you just sort of an overview of that. It will kind of show a little bit of Lewis drawing, structure drawing, and show a little bit of entering that into Spartan itself. Some of the objectives in this lab, we want you to should be able to work with Lewis structures and determine some of the implications of their properties, things like shapes, dipole moments, things of that nature. We want you to become familiar with conducting quantum mechanical calculations for a set of molecules of interest. This doesn't mean you're going to be doing a lot of math. It's all contained within the program, but you get to see some of the sorts of information that come from these types of calculations. And we also want to be able to have you draw conclusions from these calculational data about some of the properties of molecules, bond angles, bond lengths, polarity, things of that nature. In this video, we're going to assume that you already know quite a bit about drawing Lewis structures. I do a few inside of here and show you kind of how those work. It may be a little different method than you've used before. Do whatever is comfortable for you and get you to the right place. I might also point out that in this video, it's going to be like 30 minutes, but you don't have to watch all 30 minutes. It's sort of in chunks, and so you'll find out that you kind of have you have Lewis drawing and then Spartan using Spartan and Lewis drawing using Spartan. Once you get the idea of using Spartan, you're probably in pretty good shape. We're going to also show well, I just told you what we're going to show. It's going to look like this. Excuse me. We're going to draw Lewis structures for hydrogen and do some modeling with it. We're also going to work with nitrogen. All right, in here, we're going to work with this ion. I'm going to keep the same name a secret for a while, and then we're going to work with these guys down here, organic molecules. And so we're going to work with those sets in this structure. And again, it's sort of a sequence of things. So once you get the hang of using the software, you may be okay, but it's just kind of up to you. So we're going to start out. It's a series of little movie snippets I've put together about drawing Lewis structure, followed by the using the Spartan molecular modeling software. At the end of it, I give you some information about how you can actually buy a copy if you felt like it. It's like $50 to buy a copy of the software to be able to use it just for fun, which it actually is. So I'm going to go ahead and start the videos. Let's take a look at the simplest of all Lewis structures. We'll start with the molecule hydrogen gas. If you go back and think about Lewis symbols, you might recall that a hydrogen was an H and had one valence electron, so we put one dot outside of it. The other hydrogen will do the same thing with. It's fairly easy to visualize in this case that when these guys would come together, they would share 2 electrons, so that each would tend to think he had the same number as his nearest noble gas, which is helium, which has 2 electrons. We typically, in drawing Lewis structures, get away from the dot thing as soon as we can, and so we'll move over and start thinking about instead of using dots for bonds, we'll use lines. It looks something like this. So every one of these lines in here, that one represents 2 electrons. You can see this more and more as you go through. So our Lewis structure for hydrogen looks something like this. No non-bonded electrons, just 2 hydrogen electrons bonded. Two hydrogen atoms bonded to each other. This is the Spartan workspace window. It's up here. I've got it crunched down a little bit. It has other things off to the side. We don't actually care about that much at this point. But the big things you want to notice on here as you look at it are up here is an icon that allows you to build a new molecule in this structure. Over here is where you can edit one, actually a new sketch of a molecule. And if you have one already built, you want to go edit it, you can go in and do this kind of thing right here where you get to edit whatever you've got showing. What I want to do is run through the molecules that you're going to see in this short video. I'm going to start with hydrogen, kind of show you how you can build a hydrogen, how you can run an experiment. And these experiments are quantum mechanical experiments. They're fairly complicated mathematically as far as what's going on. But what they're going to do is give us some idea of what the bond lengths, the energies, things of that nature are on these different types of molecules. And so we're going to go through this kind of step by step, show you how they build, show you where the properties are, how you carry out a calculation on that sort of thing. So if I want to build a hydrogen molecule, I'll first go up here into this left-hand corner and tell it it's going to be a new build. And what I want to do is we're pretty much dealing with inorganics. The last segment we'll look at will be organic molecules. Let's deal with inorganic, and I want to look at hydrogen. Now, hydrogen from the Lewis structure is just 2 hydrogen atoms stuck together, so each hydrogen atom has one bond to it if you look in here. So if I click on this, I'll get something where I just have a 1 bond system. Now I want to switch out to being hydrogen. So I'm going to come up to my carbon. I'm going to tell it, okay, be a hydrogen. And if I click out in here, I'll see that I get a hydrogen and I have one yellow bond place sticking out in the end. And what I want to do is stick another hydrogen on the end of that. So I come across here and just click on that, and there's my hydrogen molecule. You can hold down the mouse button and you can swirl this around, twirl it. You can do all sorts of things with it. I have a a touch screen, I can actually go in and make it bigger just by spreading my fingers. I can rotate it using my fingers, that sort of thing, but you can do that with your mouse as well. If you have a scroll wheel, you can zoom it real easily, and that sort of thing. So there's my hydrogen molecule. Looks like that. Now that's just me sticking a couple atoms together. If I want to make it a little bit better geometry, I can come down here into the lower right hand corner where that green arrow is, where the cursor is, click on that, and it does what it calls minimizes, or finds sort of the best starting point for us in this experiment. Now what we do in a quantum mechanical experiment is we're going to take and do a calculation on this. And the way that will work is we come up to where it says setup, and we tell it calculations. We're going to set these up. We're going to use, for most of what we do today, we're going to use this 631G. This is just a basis set of orbitals. It's quantum, you don't really care about that, but this is kind of how we're going to do these calculations. There are different strengths and weaknesses and different types of calculations we can do. Other things you might notice about here that are helpful is the hydrogen molecule has no charge. It's neutral, so I'm going to make sure that's neutral up here. He has no unpaired electrons. They're all paired up in that bond. And so I'm going to go ahead and click on the submit button here. And when I do that, he comes in and says, well, where do you want to save it? And you can see my desktop's a mess already. I'll just save it as hydrogen. That's fine. Looks like that. And it tells me he started the calculation. It doesn't take him very long to do this. You'd be astounded at how much he's actually doing in the course of doing this calculation. He'll come back up and he'll tell us when it's finished. There it is, finished. Okay. And so I'm going to tell it okay here. And what I want to do now is I want to know something about this molecule. I want to know, for example, maybe I want to know the bond length in this molecule. And if I want to know that, I go up to where it says geometry. It's fairly evident. Geometry tells me about bond lengths, bond angles, things of that nature. So I click on this. I thought I want to measure the distance. And all I have to do then is click on one atom and then just click on the atom that I want to measure it against over here. And down toward the bottom, you'll see in the lower right-hand corner, you see the 0.730 angstroms. Okay, angstrom is 10 to the minus 10th meters. Just to kind of keep that in a perspective for you, that's a 10 billionth of a meter, so that's pretty tiny. And this is 7/10 of a 10 billionth of a meter. That's the distance between these that we've just calculated. I can also go in and look at the properties that I've calculated. So if I go up to display, up in the menu list, and tell it properties, it gives me a whole bunch of stuff. The CAS is a chemical abstracts number. The P here means I can actually dump it all into a spreadsheet, which we're not going to do this time out. The area of the molecule, kind of surface area around it, the energy of the molecule down here, and this is in atomic units. These are very, these aren't what you're used to in terms of units, but in atomic units we have electron volts. The dipole moment of this particular molecule is 0. You kind of expect that because the hydrogens will pull equally and there's no separation of charge inside of there. There's all sorts of other things along here you can look at. You can also, if you want, and as you go through the lab, you're going to be asked different things about these molecules, different things about distances, angles, things like that. So kind of take that data, record it where you need to, and then push on to the next one. You can also look at something that's kind of interesting, and that's if I look at the surfaces in here. If I look at something called the electrostatic potential map, what I'll see is it's going to show me something about electrons and where the electrons are in this type of structure. And what it shows me here is they're fairly well evenly distributed all the way around. When they aren't, and I'll try to remember to show you that in some of the others, you'll find in the red spots is where the electrons are more, you have a higher negative sense of the molecule, and where it's bluish, you have a more positive sense. Here you're kind of all kind of in this green. Everything looks pretty common in here, although you might see there's actually a little bit of a color change going across the central part. So that's just a rundown on how this would work for hydrogen. You probably know by now that not all Lewis structures work out as easily as hydrogen does, and so let's take a look at one that gets a little bit more interesting, and that's nitrogen. If you think about nitrogen as being the Lewis symbol for it is an N with 5 valence electrons. Since he's in group 5, you put 2 of these together. Again, our goal in doing these Lewis structures is to end up with 8 electrons around each atom. So it gets a little bit more of a shuffling and that sort of thing. I have an approach I like to use, very similar to what's in the book, slightly different, but pretty much what's in the textbook. And it goes something like this. Let's just write out our 2 nitrogens side by side, and let's draw a bond between them so they're hooked together. And then let's fill in electrons till they have 8 around each one. So there's 2, 4, 6, 8. So each one has 8 electrons, 2, 4, 6, 8, 2, 4, 6, 8. Everybody's got an octet. That's good Lewis structure. They're bonded together, but there's one thing I've failed to look into, and that is, well, have I counted up how many valence electrons I should actually show in here? Remember, each line represents 2 electrons. So I have a total in here of 2, 4, 6, 8, 10, 12, 14 electrons. How many should I have? Well, nitrogen, as it turns out, is in group 5, and I have 2 of those, so 2 times 5 is I should have 10 electrons in my structure. So I look at it and think about what I've got. I have 14 electrons up here, so I have to get rid of electrons. Now, it's not like I'm throwing away electrons. I didn't really have those to start with. I didn't pay any attention to how many valence electrons should be there. So what I can do is go in and throw away any non-bonded pair of electrons I want to. I can't throw away the bond, otherwise they're not hooked together. So I'm going to throw away a non-bonded pair of electrons, and to throw away a non-bonded pair, I can pick any pair I want to, but you notice once I do that, let's say I take this pair right here, and I throw him in the trash can. Okay, so he's gone. Well, that means that this nitrogen only has 2, 4, 6 around. He needs to have 8. What can I do? Well, I can share from next door. I can bring a pair over here, throw them into there, and make what we call a double bond. So it looks like this at that point. And now you'll see I'm down to 2, 4, 6, 8, 10, 12 electrons, but I'm still not all the way down to 10. So here I had 14 electrons. Here I have 12 electrons. I need to get down to 10 electrons down there. So since that made progress, I still have 8 around everybody. Let's go ahead and do it again. Let's take any non-bonded pair. I'll just take this one, throw it away, and then I'll slide a pair from here in to make a triple bond, and there's a Lewis structure for nitrogen in which I have 10 electrons, which is what I'm supposed to have, and I have 2, 4, 6, 8 around that nitrogen, 2, 4, 6, 8 around that nitrogen. So there's my Lewis structure for the nitrogen molecule, and it looks like that. Let's go ahead and build nitrogen structure inside of Spartan and see how that's going to work. We now have a triple bond, as you recall from the Lewis structure of it. If I take and go ahead and build a molecule up here in the upper left, and he's inorganic. Organics usually involve carbons, hydrogens, things like that. We're going to call him inorganic. And we're going to say that we're looking at nitrogen in particular for our atom. So what I want to do is come over here. And you might notice that in looking at my structure here, my nitrogen only attaches to one thing. And so when I look at my choices, what I'll see is that really this choice up here, the single atom attached, that seems to be my best one. So I can come over here. I can click on here, and I have 2 nitrogens now, and that's pretty much what my structure looks like. If you use your zoom wheel, or I'm using my mouse pad, or if you use your touch screen, whatever you've got, you can do that. You can rotate them around and look at them. But you might recall in our nitrogen that we had something special with that. We actually had a triple bond in between those 2 nitrogen atoms, not a single bond. And so to get triple bond inside of there, what I can do is come down below here, and where it has this, it says make bond, just click on that. And now if I'm going to make a bond, I just have to double click on one nitrogen here. Oh, wait, I don't think I got it. There you go. Right there. I don't know why it's not clicking over there. Like that. And if I rotate them around a little bit, notice now I've got 2 bonds. And so I just do that again. Since it worked so well the first time, double click over here, and now I've got 3 bonds. There's my nitrogen molecule. So I've got my N2. Notice I'm not worrying about my non-bonded electrons at all. I'm not making sure I draw those in. In this program, you don't actually have to worry about those very much, other than the fact they're going to have some role in your geometry at some point. I go down here to the lower right-hand side. I'm going to minimize this, make it the best structure I can. It'll do a fine little adjustment to it. It says, okay, that's what we look like. And now let's go do our experiment again. So I come up into my setup, calculations, and we're going to do the 631Gs. We still have no charge on this. We still have no unpaired electrons. So I go ahead and I submit. And it's going to want me to save it under something, so I'll just save it there. My desktop's getting to be a mess. We'll just do that. And so it started. My calculation started. You really can't tell if it's running as far as I can tell inside of here, but eventually we'll come back out and we'll say, okay, I'm done. Here's what we got. When are you going to do that? There we go. Comes back out, says we're done. Here's what we've got. We can again go in and measure bond length, say geometry, measure distance. If I just click on this atom, then click on this one, it tells me that's a distance of 1.078 angstroms. Remember, that's 10 billionths of a meter. If I look at properties of it, I can find out things like the energy of it, negative 108.94. They tend to go to minimum, a small energy, so more negative is smaller. Inside of here, the dipole moment 0, which again we expect because it's a homonuclear diatomic molecule. They both pull the same on there. And so you can find out those sorts of things about it. Again, you can look at the surface of it. Not particularly interesting yet. The main reason I showed you nitrogen was to show you how it is you get to add in multiple bonds. So there's my electrostatic potential map. Tell it OK. And there it looks kind of like what hydrogen did, not a whole lot different, does it? And so that's pretty much a rundown on nitrogen and how that's going to work. They'll get a little bit more exciting as we go. Let's take a look at something that's a little bit different than the ones we've seen so far. We're going to look at this guy right here. You know what the name of that ion is? Yeah, think about it. You may need to come up with it. What we're going to do is draw the Lewis structure for this and see what that thing looks like. And so we start writing it out. And you see the two oxygens and nitrogen. Nitrogen will be sort of a logical central part to this. Oxygen on each side. I draw a bond between the atoms that I've got here, and then I'm going to fill in my octets. And so when I fill in my octets, it looks something like this. Now I need to count up my valence electrons that I've got. So I think about nitrogen. Nitrogen is in, I have one of those, and he's in group 5, and so he brings in 5 valence electrons. Oxygen is, there are 2 of those, and they're in group 6. They bring in 12 valence electrons, and then since I have a charge on this of a -1, it means I have an extra electron. So I get another electron from that charge. If it was a plus charge, you'd be losing an electron. Add these guys up, I get a total of 18 electrons. That's how many I should have in my structure. The structure I drew has 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 2 too many. So what I need to do is get rid of a non-bonded pair and slide an adjacent, one in from the adjacent atom to make a multiple bond. So I could grab a hold of this atom, right, this pair of electrons here, throw them away, slide this one. Remember, these electrons are never there. I just drew them to make life easy on myself. And so when I do that, my new structure looks like this. Looks something like that. Since he's an ion, we'll take him and put him in brackets and show what his charge is up here with a -1. So that's my Lewis structure for that particular ion. Notice it's got 3 electron domains around. It has the oxygen here, has an oxygen there, has a non-bonded pair there. Also notice in this that I made the double bond on the left, but suppose I want to make it on the right. My structure ends up looking like this. Same thing really, just with the double bond on the other side of it. And that's where we get into the idea of resonance. That the real structure is going to be some kind of a hybrid of those different forms. And so in this, if you look and think about the electrons in here, if I have 4 electrons between that nitrogen and oxygen, you're probably going to make that bond a little bit shorter than what the single bond would be. So you'd expect in the real molecule to see that one bond was shorter than the other. We'll find out that that's not actually going to be the case. These 2 bonds will end up being the same length. Let's take a look at the NO2- ion. Figured out what it is yet? Inside of Spartan, and see what kind of things we can figure out about that. So if we go back and think about our Lewis structure, I come back up here to my chemical build, and what you'll notice is that it's inorganic again, and that nitrogen we had in the middle had 2 things stuck out on the side. Had a double bond stuck out on one side, had a lone pair of electrons on the center part. And so when I take a look at that, what I might think about is what I've really got in there is I've got 3 things around the central atom. I've got an oxygen have a non-bonded pair of electrons as well. And so I'm going to take a structure that looks something like, like this. Okay, looks like that. Has 3 things stuck around it. We go for, there's a couple things that have 3 around them. This is kind of, since I've got this minimized, you can't see this one very well, but that's got 4 around it. But 3 here, 3 here. See, let's just pick one and see what happens with it. So if I take this and plunk it out here, I want to have a nitrogen in the middle, so I'm going to take and put a nitrogen out here. I'm going to do a click on it, and then what we'll do, I'm going to make it a little bit bigger right off the bat so we can see it better this time. I'm going to take and put an oxygen on it, and one of those oxygens is going to be doubly bonded to it, and the other oxygen is going to be singly bonded to it. Remember that? So let's go ahead and put an oxygen here. We're going to put in, I should just change this to this, and put an oxygen over here. Now I can get rid of those extra yellow things by just hitting the eraser button here. It looks like a thumb drive to me, but it's a delete button. So you can get rid of this, and let's get rid of that other one out there. And the other thing to keep in mind about this is, okay, come on guys, let's behave, let's erase well. I'm going to erase here, there, and erase. Now you have to hit the eraser every time. See, it helps you to see me stumble through this once in a while. This is a new program for us. I'm kind of figuring some things out as we go. Looks like that. And the other thing we have in here is that in that nitrogen right here, we don't want to have that extra bond sticking in there so we can get rid of him also. See, it looks like that. Now, the thing you might recognize about this, go back and think about that Lewis structure. It had had a double bond on one side, and so what I want to do is add a bond. So I come back into here. I'm going to add a bond. Doesn't matter which oxygen I'm going to add it to. That one right there. There's my double bond, and there's what my NO2 minus ion looks like. And so if I take him and go ahead and minimize him, it looks like this. Okay. And now, if I take and do my calculation, one of the things I want to point out to you is this, is I put them into there. Let's measure the distance and see what happens. If I measure from here to here, it's 1.272. And if I measure from here to here, oh, same thing. Notice that one of those is a double bond, the other one's a single bond. You would think that with more electrons it might be closer together, but they come out the same. That's your resonance showing up. If I look at my setup for calculations on this, it's going to look like this. I want to do the same types of things we've been doing. Okay. Now this guy has a charge. He's an anion. He's got one negative charge. Be careful on this. You'd think you'd be putting a -2 if you had 2, but what you do is they call it a dianion if you have 2, and then if you go to 3, then they call it -3. So you have to watch that. This is going to be an anion, only has one charge on, no unpaired electrons. We'll go ahead and submit this thing, and we'll call him, okay, I'll give it away. He's called the nitrite ion. I'll save him in here. He started my calculation. And hopefully pretty soon he'll be finishing my calculation. Come on, guy, you can do it. It's a little more complicated sometimes with ions. And there he is. Okay, so there's my structure. Now I can measure those interesting things. So for example, if I wanted to measure the bond lengths again, see if they changed at all, I could go to geometry. They were 1.272 before. I'm just making that up. I think that's right. And they're 1.229. They went from 1.272 to when they dropped a little bit. This is a more sophisticated calculation, but you will notice that no matter what they did, that those two bonds are the same length, even though we represent it like this. That's what the resonance hybrid kind of is all about. We can't represent the true structure by one Lewis structure, so we have a couple of them together and say, okay, it's some sort of a hybrid of these. We can also measure a bond angle. When I measure an angle, what I do, and this is easy to know which angle, I only have one, click on one of the outside atoms of the angle you want to have, and then click on the central atom in that angle, and then click on the last atom in there, and down below you see the angle, and there's 116.70 degrees. You notice this structure is pretty flat. I mean, it has to be flat. He's three atoms. Sorry, I lost my mind. And so he looks something like that. If I want to look at properties on here, I can go to Display, Properties, and here are my energies. HOMOs, they're called a highest occupied molecular orbital. You may run into that in class. Notice he has a dipole moment of 0.58 dBi. That shouldn't be too surprising to you for this kind of a molecule, because he's got a nitrogen bent, oxygen's bent off of that, and we can actually display the dipole vector, which is sometimes pretty good visually for you to help see things. So if I do it like this, here's what happens. This arrow, it really looks like one coming out of a quiver to me, but this guy right here is my dipole moment vector. He's pointing toward the oxygens on this side. Oxygen is a little more electronegative than nitrogen. It's got a couple of them here. You have a lone pair of electrons up here. My positive end is here. My negative end looks like that. My nitrite ion has a dipole moment that looks like that. So you can actually visualize that as well. Let's look at a few organic molecules, those comprised of carbon, hydrogen, sometimes oxygen, nitrogen, sulfur, things like that, and see what happens with those. We're going to look at three in particular. This one is C2H6. We're going to look at C2H4 and C2H2. And this is called ethane. Organic folks have a different way of naming things than what you're used to. This guy is called ethene, or sometimes ethylene. And this guy over here is called ethine, or maybe more commonly known as acetylene. We go to draw the structures. Notice all the hydrogens. Hydrogens have to be around the outside, so I have to be stuck with carbons in the center part here. And I'm going to put 3 hydrogens around each one because it makes it look nice and symmetric. Looks like that. If I count up my electrons in here, I have 14 electrons in that structure. If I look at how many I should have, carbon is in group 4. and I have 2 of those, so let's bring in 8 electrons. Hydrogen is 6 of those, and group 6 gives me 14 electrons, so I match up, and so there's my Lewis structure for ethane. Okay, it looks something like that. If I look at ethene, what I'll look at is the same starting point, except I have fewer hydrogens, so I'm going to have only 2 on each carbon. And then when I go to fill in my octets, like we've been doing, you'd say, well, I have to put one there and put one there. But now when I do that, I have 2, 4, 6, 8, 10, 12, 14, and I still have 14 electrons, but how many should I have? The carbon has 2 times 4 is 8. And my hydrogens, I only have 4 of those, times 1 is 4. I should only have 12 electrons. I have too many electrons. And so what I do is make an adjustment. I get rid of a lone pair here, slide one in from the side, and my structure ends up looking, I'm going to cheat over here and go to ethine a little bit, is going to look like this, and has that double bond in the middle. And that's what my ethene structure looks like. That's that one over there. If I go to ethine, it's been going so well with these two, kind of keep the same idea. I only have 1 hydrogen on each carbon, so I fill in octets like that, but now I've got 2, 4, 6, 8, 10, 12, 14 electrons still in here. But how many should I have? I have 2 carbons, which each bring in 4 electrons, gives me 8. And I have 2 hydrogens, each brings in 1, gives me 2. I should have 10 electrons, but instead I have 14 again. So I have to get rid of 2 pair of electrons. The way I can do that, I'll go up here with it, is I can take and get rid of one of those lone pair, slide one in from next door, and I get this. And I've still got too many electrons, so I just do it again. Slide out of here, slide into there, and I end up with a triple bond in the middle. One of the things you might pay attention to is if I have more electrons between those 2 carbons, you might anticipate that those bonds might get shorter because the electrons tend to hold them together. Let's look last at those 3 organic molecules and see if we can figure out something about how to draw those things inside of here. So one of them was ethane, C2H6, and if I go up here and click on my organic, you'll find if you go to ethane, it had a central carbon. It actually had a single bond and then had 3 hydrogens around. It looks just like this first thing I have up here in my template. If I just click out here, there's my carbon with those things in it. Now I have another carbon attached to it just like that, and all I have to do is come out here and click on the yellow, and there it is. And then I want to go and put my hydrogens ions in. I think there might be easier ways of doing this. I'm not going to try right now because I'll just confuse you more than I already have. And so if I go here and look at hydrogen, I can click on that. I can click on this. I can click on this one, click on this one, click on that one. I think there's an automatic way of doing this, but I haven't quite figured it out yet. It looks like that. And so there's my ethane molecule. He looks like that. I can take him and I can minimize him. Okay, and I can go through the whole set again of doing calculations and doing things like that. Find out what his minimum energy looks like. You know, it's kind of neat if you look down here how these guys are trying to avoid each other down that central axis. You got this guy up here, this guy's opposite. They kind of spun around. That's an organic thing. You'll hear about that later. Now suppose I want to draw the ethene, the one with the double bond in it. So let's go ahead and we'll just build a new molecule from it and say we're going to go to organic. And now what I want to do is in my ethene, I have a double bond and 2 singles, so I just click down there, click over here, so my 2 carbons are doubly bonded, and then I can go back in and put in my hydrogens, like I was doing before. Click, click, click. Well, let me get it down a little bit. Click, click. If you ever have trouble getting things stuck on them, just move them around, rotate them until you get a good clean shot at it. And there's what my ethylene molecule looks like. Okay, it looks like that. And I can take that and I can minimize it as well, and then you can go through and do your experiments on it the same as you did before. And then doing a triple bond just really isn't any worse at all. If I come into here, I'm going to look at having a triple bond, although the part I don't understand is how I'm going to get this thing to work out. There we go. I'll move him a little bit bigger. I'll do a new build, triple bond, boom, boom. Okay, and I can rotate them around if I want to, and I can go ahead and stick hydrogens on them. And then you can do whatever you want to do in the way of calculations, in the way of geometry determinations, anything at all you want to do with these molecules you can do. So it's not a terribly difficult program to use. I think you'll find some interesting things in it. We'll look at particular aspects. We're not going to look at the whole thing. It's a lot more powerful than we're showing you right now.